In this video, we are going to discuss precipitation reactions. First, we're going to define what a precipitation reaction is, and then we're going to learn how to write a correct molecular equation, total ionic equation, and net ionic equation for any precipitation reaction. So first, what is a precipitation reaction? Well, it's a process in which you have two soluble reactants. Generally, they're two ionic compounds as your reactants, and they react to form at least one insoluble product, which then will fall or precipitate out of solution. As I mentioned, most precipitation reactions, the reactants are ionic compounds, and the products are also ionic compounds, but at least one of those products is insoluble. So let me show you just a short little video illustrating a precipitation reaction.
The first precipitate will be produced from aqueous silver nitrate and aqueous sodium chloride. Aqueous sodium chloride is added to the silver nitrate solution. We observe a white precipitate of silver chloride. This heavy precipitate thickens and falls to the bottom of the test tube as more aqueous sodium chloride is added to the silver nitrate solution. This is a white precipitate of silver chloride. Again, we take aqueous silver nitrate. This time we are going to add aqueous sodium iodide. When the sodium iodide is added to the silver nitrate, we get a pale yellow precipitate of silver iodide. Note that this precipitate is not the same color as white silver chloride. It is very pale yellow or cream-colored. The cream silver iodide falls to the bottom of the tube and begins to form thick lumps.
So a precipitation reaction is also called a double replacement reaction. You may also hear it called a double displacement or a metathesis reaction. And these double displacement reactions follow a general format. So let's take a look here. We have our two reactants, AB plus CD, where A and C are the cations. Of course, they're written first, and B and D are the anions. In a double replacement reaction, essentially the two anions switch places. When that occurs, you end up with cation A pairing with anion D, so you form AD, and you have cation C pairing or combining with cation B. And again, if one of these, at least one of these is insoluble, then you have a precipitation reaction. So take a look at these two reactants, sodium chloride, aqueous or soluble, and silver nitrate, which is soluble. Let's see if you can predict what the products would be for this double displacement reaction. So if sodium is my cation, chloride is my anion, over here we have silver is my cation, nitrate is my anion, then my anions are going to switch places, and I'll end up with sodium pairing with nitrate and silver pairing with chloride. And if I review my solubility table, so open up your text and look at your solubility table, you'll see that sodium and nitrate compounds are soluble, whereas silver chloride is insoluble. So this would classify as a precipitation reaction. Now what we have here, this complete balanced equation for a precipitation reaction is called the molecular equation. Even though these are ionic compounds, it's still called a molecular equation. So let's review the rules for writing a correct molecular equation for a precipitation reaction. So let's say that we start with potassium chloride and lead 2 nitrate. First thing we need to do is predict the products. So you'll take only one of the first cation and match it with only one of the second. And then you'll take, and of course you write the cation first, then you'll take only one of the second cation and match it with only one of the first cation. So let me show you what I mean. So if we have potassium chloride and lead 2 nitrate, we'll take the potassium, and even though we have 2 nitrates over here, you see we have 2 nitrates, we're going to pair only 1 to 1 to begin with, 1 potassium with 1 nitrate, and we're going to pair up one of our lead 2 cations with one of our chloride ions. So pair them up 1 to 1 first. In the second step, now we need to take into account the charges and pair up the ions, or pair up the ions based on their charges. So look at our two products that we wrote. The potassium nitrate. The potassium's a +1 and the nitrate's a -1, so these will combine at a 1-to-1 ratio. The lead has a +2 charge and the chloride a -1. So this, we have to add another chloride to pair up with our lead 2. So we would, now in the second step, we pair them up based on charges, or we write the correct formula for each of our products. In the third step, now we have to balance the equation. Okay, so here's our equation thus far. We've correctly predicted the products and written the correct formula. Now we have to balance the equation. You can see we have 1 potassium, 1 chloride, 2 chlorides, 2 nitrates, and 1 nitrate. So we have to add our coefficients, and we can only add coefficients to balance. So we add 2 in front of the potassium chloride and 2 in front of the potassium nitrate, and then we have a balanced equation. So remember, when you balance in the third step, we can add coefficients. In the second step, we added subscripts to pair our cations and anions up in the correct ratio. In the fourth step, we need to consult our solubility rules and assign the correct solubility state. So take a look at your solubility rules, and potassium nitrate, that's going to be soluble, so we'll put an AQ after that. The lead chloride, that is insoluble, so we'd put an S to indicate that that will form a solid precipitate. So our final equation, we would predict the products, we would pair up the correct anion and cation, then we arrange them so they have the correct number of cations and anions based on their charge. Then we balanced the equation, and then we predicted the correct solubility. So be sure to carefully follow those steps, write them down, and every time you solve a problem like this dealing with molecular equations, you want to follow those steps. So here's two problems. Again, be sure you have those steps written down and use those steps to predict the products and write a complete balanced molecular equation for the following two. So pause the video and give it a try. Okay, so let's take a look at the first one. For the first one, the first thing I want to do is pair up the correct cation with the correct anion. So I'm going to take 1 sodium and 1 chloride. Again, it doesn't matter that I have 2 over here and 2 here. I take 1 sodium cation, 1 chloride, and then I take 1 copper and 1 carbonate and pair those up. Again, the cation is always written first. Now the second step, I want to check to see if I need to write the correct formula, if I need to add any more a subscript so that the charges add up to 0. Sodium is +1, chloride's -1, so that's correct. So I don't need to write any subscripts there. In this case, the copper is a +2 and the carbonate's a -2. So here I don't need to put any subscripts. So the next thing I have to do is balance the equation. I see that I need to add 2 sodiums, so that gives me a complete balanced equation. And now I need to consult my solubility rules to check for solubility. Sodium chloride is soluble, so I put the AQ. Copper's carbonate is insoluble, so this would be a precipitation reaction. Let's take a look at the second one. First, we want to be able to write the correct chemical formulas, so be sure you review how to write the correct chemical formula. So for this one, you can see potassium phosphate. Here's our chemical formula. Magnesium chloride would be here. So our first step, I'm going to pair up the potassium with the chloride. I'm going to take one potassium and pair it with one chloride, one magnesium with one phosphate. Again, I'm not concerned about the charges just yet. Okay, so I paired up magnesium and the phosphate, potassium and the chloride. Now the second step, I look at the charges. My magnesium is a +2 and phosphate is a -3. So I'm going to have to pair those up. I'm going to have to put a 3 subscript and a 2 for the phosphate. So each magnesium has a +2. I need 3 of those. My phosphate's a -3. I need 2 of those. So this would be the correct chemical formula for magnesium phosphate. Potassium's a +1, chloride's a -1, so that's fine just the way it is. Now I need to balance the equation, so I put in coefficients now to balance them. In this case, we would end up with 2 here, 3 magnesium chlorides, and 6 potassium chlorides. And finally, I look at the solubility rules, which tell me that magnesium phosphate is insoluble, so I put a S for solid state, and the KCl, potassium chloride, is soluble, so I put an AQ. So we showed you how to write the molecular equation for a precipitation reaction, but this is not always the most accurate way to represent a precipitation reaction. As you can see, some of these compounds, the sodium carbonate, copper 2 chloride, and sodium chloride, these compounds are aqueous and therefore soluble, which means they exist in a dissociated form. So they really exist separated into their ions rather than together as we're showing here. So it's more accurate to write these things not as you see here in the molecular equation, but to write them as dissociated ions, since that's how they actually exist when they are in an aqueous solution. So the equation which shows these strong electrolytes in their dissociated form is called the ionic, or sometimes the total ionic equation. So let me show you how to write a total ionic equation. Here we're given our molecular equation. This is the balanced molecular equation. And we want to take each of these soluble reactants and then the soluble product and write it in its dissociated form. So you might want to review the video on solubility, but that's essentially what we want to do here. So let's start with our sodium carbonate. The sodium carbonate actually dissociates. We have 2 moles of sodium ions, 1 mole of carbonate ions, so we're going to write it in its dissociated form. Now remember, don't write sodium as Na2+. It's 2 Na+, 2 moles of sodium ions, not Na2+. Then we write the copper chloride. We have 1 mole of copper ions, 2 moles of chloride ions, and again, be sure to write the chloride as 2Cl-, not Cl2-. That's incorrect. Then we'll write our product, our sodium chloride. We have 2 moles of sodium ions and 2 moles of chloride ions in the dissociated form. And the copper carbonate is a solid, and so it does not exist in its dissociated form. It actually precipitates. So be sure when you write your ionic equation, you include the correct number of ions, the correct charge on the ions, and whether it's aqueous or solid. So remember all of those things when you're writing your equations. So in general, the steps to write a total ionic equation, you must first, of course, write the correct balanced molecular equation. Then anything that's aqueous, any strong electrolyte, such as soluble ionic compounds or strong acids, you write in their dissociated form. Remember the charges, remember to write the correct number of ions, and remember to write whether it's aqueous after it. And then anything that is a solid, liquid, or gas that's formed as a product, you write in the undissociated form, so you don't split it into its ions. So here, again, you're given the molecular equation. Pause the video and see if you can write the total ionic equation for this reaction. Okay, so first we're going to take a look at all of our soluble ionic compounds. We're going to write them in their ionic or dissociated form. For potassium phosphate, we're going to get 6 moles of potassium ions. We're going to get 2 moles of phosphate ions. Remember, the charge is in aqueous. For magnesium chloride, we're going to get 3 moles of magnesium ions, and we're going to get 3 and 2, that's 6 moles of chloride ions. Again, all of these are aqueous. Our magnesium phosphate is a solid, so we're going to write it just as is since it does not break apart into ions. And then our 6 moles of potassium chloride, that's going to give us 6 moles of potassium ions and 6 moles of chloride ions. So be sure to examine this and be sure you've included everything, correct charges, everything is balanced, and all the states are correct. Now, one last type of equation that we mentioned we want to look at is a net ionic equation. It's basically just a simplified version of our total ionic equation. So first thing, you write the total ionic equation, and then you cross out anything that does not change from the left side to the right side. The only thing left are those things that react during the course of the reaction. And anything that did not change, any ions that were the same, that were soluble as reactants and soluble as products, we call those spectator ions. So let me give you an example. Here we have a molecular equation. We showed you this one earlier. If we wrote the ionic equation, we showed you it would look like this. And then the net ionic equation, what we would do is we would look at our ionic equation and we would look for any ions that did not react. So here I can see that I have 2 moles of sodium ions on the reactant side, and I also have 2 moles of aqueous sodium ion on the product side. The sodium did not react, it's just a spectator ion, so we can cross those out. Other than that, we have the chloride ions. We have 2 moles of aqueous chloride ions as a reactant and 2 moles of aqueous chloride ions on the product side. Again, those are aqueous on both sides. They did not react. So those are spectator ions, and we can cross those out. The carbonate ion, the copper 2 ion, those did combine to form an actual product that precipitated out. So those are not spectator ions since they did actually react. So we just rewrite this this ionic equation and leave out the spectator ions, and we would have a simplified version called the net ionic equation. And again, you can see this is it's a balanced chemical equation as well. So to write the net ionic equation, first thing we want to do is, of course, write our balanced molecular equation. Then we want to write our total ionic equation by dissociating all the strong electrolytes. Then we cross out anything that remains unchanged, our spectator ions on the left and right side, leaving us with just our ions that physically reacted. And that's our net ionic equation. So let's take a look at one last problem. Pause the video and see if you can write the molecular, ionic, and net ionic equations for the following reaction given the 2 following reactants. Pause the video and give it a try. So first step, we want to pair up the correct anion and cation, one of each, one ammonium with one nitrate, one zinc with one phosphate. Next, we need to look at the charges and write the correct chemical formula based on the charges. Ammonium's a +1, nitrate's a -1, so that's correct. Zinc is a +2, phosphate's a -3, so we have to balance the charges with the subscripts 3 and 2. Now we can balance the equation using our coefficients. You can see we have those here. Again, if I'm going too fast, pause the video and be sure you can see this for yourself. And finally, we need to write the correct phases. Our solubility tells us that ammonium nitrate is soluble and zinc phosphate is an insoluble precipitate. Now we need to write our ionic equation. So for each reactant that's aqueous, that's a strong electrolyte, we need to write it in its dissociated form. So we have 2 and 3 here. So we have 6 moles of ammonium, aqueous, and 2 phosphate. So this dissociates to give us 6 moles of ammonium, 2 moles of phosphate. Here, the zinc nitrate dissociates to 3 zincs and 6 nitrates. And our products, our ammonium nitrate is soluble, so we get 6 ammoniums and 6 nitrates. And the zinc phosphate, of course, is insoluble, so it does not dissociate. And then finally, we cross out our spectator ions. If we analyze these, we should be able to see that the ammonium, that does not participate in the reaction, and neither does the nitrate, so we can cross those out. Once we've crossed those out, we write what we have left, and we have our net ionic equation of 2 phosphates, aqueous plus 3 zincs. Aqueous gives zinc 2 phosphate, solid. Now, it doesn't matter what order you write these in. So be sure that you can write the molecular, ionic, and net ionic equations for any double displacement reaction.